Welcome to Exploring Computing.
The topic of this video is how AI is actually done. The goal here is to demystify AI by giving you a concrete example of how it works. I'll do this by first showing you an example of an AI spam classifier and the data needed to train the classifier. I'll then go into how it works by breaking down the theory behind logistic regression and generalizing that into an explanation of neural networks. Finally, I'll talk about the role of AI engineers and how AI is done in practice. So let's look at a spam classifier. I've previously mentioned email spam classifiers, but the one we're breaking down today is going to be for text messages. Recall that the goal of a spam classifier is to take in a message and determine whether it is spam or not spam. What we're looking at here right now is the data that the AI is going to be trained on. It consists of many text messages as well as whether they are spam or not spam. Each enumerated item here is a training sample that consists of the text message as well as a classification of whether it's spam or ham. In this case, ham means it's not spam. For example, for the 10th item, we have the message, had your mobile 11 months or more, etc., and it's classified as spam because it's not from your friend, it's just from someone or some corporation that's trying to sell you something. Now, on the other hand, we have an example here where it says, I've been searching for the right words to thank you for this breather. I promise I won't take your help for granted, so on and so forth. And that's classified as ham because that is a legitimate text message from someone that you might know. Now, this is just the training data, which is why we have the right answers like ham or spam already in place. However, the goal is that we will use this data to train the AI, and eventually we'll be able to just put in the text message and the AI will tell us whether it thinks it's ham or spam. And the AI should be able to do this not just for the messages that it has already seen, but for any message. So in order to train the AI successfully, it needs to see a lot of samples. So just to give you an idea of the scope of how much data it needs, let's scroll down and just look at all of the data. All of these have been labeled, and all of these are messages. And you'll see that there's about 5,000 of them. This might seem like a lot of data, but honestly, it's considered a relatively small data set. And the reason we can get away with using something that's relatively small is because this is a really simple problem. More complicated AI problems, such as Face ID, which takes in a video and determines whether it's the right person or not, require training data on the scale of hundreds of thousands to even millions of training samples. Since the message that we have contains both the message as well as the correct classification, we can model this as a supervised learning problem. In this case, the X's would be the messages and the Y's would be whether it's spam or ham. And so I just built a really simple logistic regression classifier, which I then trained on the data. And so let's see it in action right now. So first I need to load the model that I just trained by doing import spam. And then I type in what I want to classify. So I just use the model that I wrote, writing spam, and I write classify. And I put in a message that I just sent to my roommate a few days ago. So I said, also, I made some coconut pudding. Feel free to take the one in the glass yogurt container. And the model should tell me whether or not it thinks it's spam or not spam once I hit enter. And as you can see, it thinks it's not spam. Now I'll do the same with the message that my roommate replied to me, and she wrote, "Oh, thank you." And as you can see, the model thinks it's not spam. Now let's test this model on a text message that is spam. So I received this message from a while back from a boba shop, and as you can see, it is a spam message. It's not from someone that I actually know. And as you can see, the message classifies it as spam, which is what we expected. Of course, this model isn't perfect. It sometimes makes mistakes too, but it actually works pretty well. So let's break down how this thing actually works. And we'll do that by starting with a very simple example. And I promise it'll generalize very easily. Suppose you're working for a car insurance company and you want to assign a good driver score bonus to drivers applying for insurance. You want to base the score off of the number of years of driving experience as well as the number of accidents a person has been in. So the inputs to this model would be the number of years of driving experience, which we'll call E, as well as the number of accidents that a person has been in, which we'll call A. And we want our model to predict a good driver score, which we will denote as Y. And note that this should be positive if the driver was a good driver, and negative if the driver was a bad driver. And the data that we have will be a past record of how scores were previously assigned based on the inputs. And this might look something like this. So the horizontal axis corresponds to E, which is the years of experience a driver has, and the vertical axis corresponds to A, which is the number of accidents. So, for example, this point over here might correspond to someone who has 10 years of experience and only one accident, whereas this point over here might correspond to someone with 1 year of driving experience and having had 10 accidents. And for each of these points, we've color-coded and marked them so that they correspond to the driver score that they had received. So, for example, this person who had driven 10 years with only one accident was a good driver, which is why they received a positive score, and it's red, whereas this person who had only driven 1 year but had 10 accidents must have been a terrible driver, and so he got a negative score as well, and that's why it's marked as blue. Now, the goal of the learning algorithm is to figure out, based off of all of this data and past experiences, if, for example, it received a point here, which might correspond to someone who had driven for 9 years and got into 2 accidents, whether or not it should be a positive score or a negative score. And as humans, we're able to kind of tell immediately off the bat that this should be a positive score. But we want the computer to be able to figure that out too. Now, as you can tell from the title of this page, the technique that we're going to use is called linear/logistic regression. The difference between linear and logistic is not super important, but just know that the reason why we call it linear regression is because it's linear, which means line. We can draw a line between all of the points that we're trying to separate. So in this case, we can see that the line would look something like that. And there is that one point that falls on the wrong side of the line, but that's okay. The model that we train is not always perfect, and perhaps even the person assigning that score might have messed up. It doesn't matter since our model would be working most of the time anyways. Now let's do a quick refresher on some math that you might not have thought about in a really long time. So remember how a long time ago you were once taught that the line is represented by y equals mx plus b. And we were told that m represents the slope of the line and b is equal to the y-intercept of the line. And so what you would do with this equation is you would plug in an x and you would get an y. Well, now we want to find a similar equation, except now instead of just plugging in a single x, we actually have two things to input, an e as well as an a. And so what we want to do is we want to modify this equation so that it can take in two different things. So in this case, m and b are constants. And so just because we'll be adding in more constants, let's rename them into C0 and C1. So we can rewrite this y as y is equal to C0 plus C1 times x. I kind of switched the order between the two terms, right? This mx, which is now C1x, I moved to the second, whereas this b, which is now C0, I moved to the first. But also notice that there is no variable that will input that's actually called x, right? We only have e and a. So let's replace this x as e instead. In addition to that, our formula also needs to take into account a. And so we'll just add that into the equation by giving it an additional constant, which we will call C2, which is multiplied by A. And so the goal of linear regression is to figure out what these constants, C0, C1, and C2, should be so that we obtain this nice line over here. And the way that this is done is first by randomly picking values of C0, C1, C2, and then changing them a little bit and checking to see if it does better. And if it does better, then you keep on changing it in that direction. And if it does worse, then you change it in the other direction. So for example, if we first started with a guess that C0 was supposed to be 200 and C1 was 100 and C2 was 0, and then you would plug in all of the data points that you already have to test if it works well. And if it doesn't, then you might tweak it so that C0 is now 201 and C1 might be 101 and C2 might be 1 instead of 0. And you would just repeatedly try different combinations of C0, C1, and C2 by changing them a little bit at a time until you get a nice line that looks something like that splits up all of the points that you already have from your data nicely. And because computers are so fast, you're able to try out a bunch of different combinations of C0, C1, and C2. And so eventually you'll be able to find something really nice. So in this case, the computer might have picked 0 for C0, 50 for C1, and negative 100 for C2 as what would have best fit the data that we had. And so the resulting equation would be y is equal to 0 plus 50e minus 100a. So let's check how well this model fits the data that we trained it on. So let's look at this point over here, which corresponded to a driver who had 10 years of experience and 1 accident. So E would be 10 and A would be 1. And so plugging that into the formula that we have, we would get 0 plus 50 times 10 minus 100 times 1, which is equal to 0 plus 500 minus 100, which is equal to 400. And that fits our model because 400 is positive and this point was positive as well. So let's try it with a not so good driver. So remember this point over here where E was 1 and A was 100. Let's see how that fits into the model. So plugging those numbers into the equation, we have 0 plus 50 times 1 minus 100 times 10, which is equal to 0 plus 50 minus 1,000, which is equal to negative 950. And that matches our model as well, because negative 950 is negative, which is exactly what this point was supposed to be. And now we can apply this model to points that wasn't even in our data to begin with. So do you remember this point over here, which wasn't in our data and we were just wondering what it should be? Well, now we can plug it into our model. So this corresponds to E being 9 and A being 2. So let's plug it into our model and see what happens. So the equation would be 0 plus 50 times 9 minus 100 times 2, which is equal to 0 plus 450 minus 200, which is equal to 250. And this number is positive, which means that this should be positive as well. Just as a disclaimer, these numbers, 0, 50, and negative 100, might not actually be the most optimal numbers, but the goal of logistic/linear regression would be to find what these actually should be. And just for the sake of this example, these worked pretty good. And so that's why I just assumed that this is what linear or logistic regression would find. But they can be really fine-tuned and even find numbers like, 0.002 and 52.1, and that would probably give a better fit. And so I actually highly recommend playing around with changing around these numbers over here just to see how it might actually affect this line over here. But as a summary, basically what linear regression does is it tweaks these constants over here until you get a nice line that fits your data. And because computers are so fast and powerful, it's able to try out a whole bunch of values so that the values that you do get are very optimal. Now, in the previous example, we only had two variables, A and E. And so those would have been the X's. But the model that you just learned can actually be generalized to any number of variables. So let's say we had the variables x1, x2, x3, so on and so forth, xn. Then the linear regression model would basically find the constants for all of these variables. And so the resulting model would look something like y is equal to c0 plus c1 times x1 plus c2 times x2 plus c3 times x3, so on and so forth, plus cn times xn. And the goal of the model would be to find the C0, C1, C2, C3, C4, so on and so forth up until Cn that is the most optimal. And so as you can tell, the more complicated a model is, the more C's or constants you would have to find. And typically a more complicated model would require more data just because there's more constants that need to be found. And finally, the last thing to note is that logistic regression actually adds an additional component called the sigmoid function. And so instead of directly using this value that we have obtained, we actually pass this value through what we call a sigmoid function. The sigmoid function, which we'll call g over here, is given by the formula 1 over 1 plus e to the negative xth power, where e is Euler's number, which is approximately 2.718. And so for logistic regression, the prediction that you make is actually given by the formula y is equal to g with the value that we have up here passed in. So it'd be g with C0 plus C1 x1 plus C2 x2 plus so on and so forth passed in. And that's equal to 1 over 1 plus e to the negative C0 plus C1 x1 plus so on and so forth. And the important thing to know about the sigmoid function is that it looks something like that. If we were to graph it out, and this was x, and this was the sigmoid function, then it would actually decrease to 0 for values that are very small, so very negative numbers, and it would asymptotically increase to 1 for values that are very large. So let's just draw out that asymptotic line. This would be 1. So, for example, if this sum over here was a very large number, like 5,000, then it would probably be something like 0.999, where it's very close to 1. Whereas if this sum over here became was a very high magnitude negative number, like negative 200,000, then it would be very, very close to 0. And the reason why we would want to use the sigmoid function is because it limits everything to between 0 and 1, and that's very helpful when we're talking about probabilities. And so if the problem was something like, how likely is this message a spam message, then we would be able to use the sigmoid function to get a number between 0 and 1 that represents the likelihood that the message is spam. So that's cool. Linear regression and logistic regression seems to allow us to take in any number of inputs and give an output that seems to fit well. So why would we ever need neural networks? I encourage you to pause this video for a few seconds and take a guess. I hope you had a chance to do that. Well, the answer is sometimes linear regression doesn't work. For example, what if we can't draw a straight line or a linear line between the positive and negative scores? So let's consider this following problem. It's a similar problem to earlier. We're still trying to figure out the good driver score. And we also want to consider the years of experience of the driver, which we call E. But now instead of the number of accidents that the driver has been in, we are considering the age of the vehicle, which we're calling V. This is the data that we're working with, and it looks a little bit different from earlier because we want a negative score for experienced drivers with a newer car because newer cars are expensive and wrecks are more expensive. But we also want a negative score for newer drivers with older cars, since older cars have less safety features. And so you'll see that we have a bunch of positive scores here, but we have these two groups of negative scores. And so you'll notice that no matter how you draw the line, whether it's like this, or like this, or like this, you can't cleanly split these two groups of points apart. So let's backtrack for a second. Remember how we're able to express the logistic regression model as the formula y is equal the sigmoid function with C0 plus C1e plus C2v passed in, where we have e and v as inputs and y as an output? Well, if you remember from the previous video, we can actually represent this model as a picture as well. So we would have the inputs e and v, and it would get passed into the function, which we would express as a square, and it would output y. And this function over here is exactly g c0 plus c1e plus c2v. And we also talked about how this unit over here looks like a neuron, where this part is the dendrites, which takes in the outputs of other neurons, and this part would correspond to the axon, which passes on the output of this entire neuron to other neurons. So we can use that idea to chain a bunch of these units together. And so one way that we can chain this together would look like this. We have three similar units that are chained together, and the units in the first layer all look very similar to this because they both take in E and V, and this one also takes in E and V. But this one's a little bit different because it's in the second layer. So instead of taking in either E or V, it takes in the outputs of this one and this one. And this gets passed in through a similar logistic function that looks like that and outputs our final answer. So zooming into the picture a little bit, we have three neurons, 1, 2, and 3, and they're laid out into two layers. In the first layer, each of these neurons have the input E and V, and you can see these over here. And they each have their own logistic function. So here we have the sigmoid function that has C0 plus C1e plus C2v passed into it. And here we have a different logistic function where the sigmoid function has C3 plus C4e plus C5v passed in. Note that these constants are different, right? Here it's C0, C1, C2. Here it's C3, C4, C5. And then in the second layer, we have its own logistic function, but now instead of having E's and V's, we have Y1 and Y2, which is what was passed into this second layer over here. And in this logistic function, we have the constants C6, C7, and C8. And so what neural networks do is they do the same tweaking that we've mentioned earlier, where it kind of changes the values of all the constants until it finds something that is optimal, but it has way more than what it needs to do before, right? It needs to figure out C0, C1, C2, C3, C4, C5, C6, C7, and C8. And as a consequence of that, we need a lot more training data to figure out all of these constants. So the pros of using a neural network is it allows you to chain together multiple logistical functions. And so by doing so, you actually obtain enough flexibility that your model no longer has to just be a straight line across all of the data. And that's extremely powerful. However, the con to that is you actually need a lot more data to train something that's a little bit more complex. And finally, we mentioned before that each logistical unit can actually take in any number of inputs, right? We were able to take in, x1, x2, all the way to xn, where n is any number. And so what that means is we can actually chain together all of these things in any way we want. And so let's say we had two inputs, E and V, which are the same as before, but let's say we wanted to have 5 different neurons in the first layer. And so we could easily do that, where each one of those circles represents a logistical function, and we would just pass it in to every single one. And let's say if in the second layer we wanted 3, then we would pass in the 5 outputs from the previous layer into each one of the 3 neurons of the next layer. And I'll just do ... because that's a lot of lines. And we could, go back to 4 and so on and so forth. And so this is actually an extremely flexible structure, which is why this has been such a big deal. So to see a neural network in action, I highly recommend you checking out the website playground.tensorflow.org. TensorFlow is a library that allows you to implement neural networks, and this page allows you to visualize how a neural network works. And so you'll see over here, we have a neural network that has 2 layers. So in this case, the first layer has 4 neurons and the second layer has 2 neurons. And this is the data that it's being trained on. And since it hasn't been trained yet, the background here is all hazy because it doesn't know what the right answer should be. And over here, we have the different data sets that you can train your neural network on. Let's start with this one because it's the one that's the most similar to what we had earlier. And let's begin by visualizing logistic regression. So remember how logistic regression can be represented as a neural network with just one hidden layer and only one neuron in that layer. So once we hit that play button, it starts training it. And as you can see, it was trained really quickly because this graph on the right stopped changing as much, and as well as this training graph over here got really low and it stopped changing. And so you'll see over here that these clusters of points over here were our original data set that we trained the model on, and this shaded background is what the model is now learned. So in this case, all of this area over here that's shaded orange will be predicted to be orange by the model, whereas everything over here would be predicted to be blue. And so you can see over here that it actually perfectly predicts all of these orange points should be orange, and it perfectly predicts that all of these blue points should be blue. And it works for points that you haven't seen too, right? So for example, if you saw a point that was like somewhere over there, it would also be considered orange. But now let's see what happens if we tried this on a more complicated data set. So let's reset the model. And you'll see that on the right over here, it's basically stopped improving, and so that means that it's done being trained. But you'll see that this model that's being shown does not accurately predict this data over here. And notice that this data is very similar to that second example that I showed you. And so now the model for all of this area will predict orange with somewhat high confidence because it's a brighter orange, whereas over here it would predict blue with somewhat lower confidence. And so this model doesn't do very well on any of these points because it would have predicted blue when it should have predicted orange. And so, as we've mentioned in the lecture earlier, in order to remedy this, we can use a neural network by making this more complicated. So we'll increase the number of neurons in the first hidden layer. And this isn't quite the same model that I explained earlier, since that model actually had an additional layer to this, but we can see what happens when we just have one hidden layer with 2 neurons, and you'll see that it has converged. And in this model, it would predict all of these points to be orange, and all of these points to be orange, and all of these points in the middle to be blue. And it does pretty well, except for these little small areas over here. It actually does really well. However, the cool thing is you can actually mouse over these points, and you can see what each of these neurons are doing and how they're contributing to the understanding of this entire model. And so you see that this first one helps figure out whether or not the points are over here, and the second one helps figure out whether the points are over here. And so with the two combined, we get the model that we want. Now, once we see what these two neurons are actually doing, what a AI engineer might think is, okay, so they're trying to figure out which corner is each set of points on. And so what might make sense is to actually use 4 neurons so that each corner can be covered. And so that's what I will do right now. Increase the number of neurons, reset the model, and once I start training it, you'll see that it does exactly what we want it to do. Each neuron tries to determine which corner the data point is on. And this is great, but we'll see that on some data sets that are even more complicated, this just simply isn't enough. So now let's play with a more complicated data set that looks all spirally. And once we hit train, you'll see that it just doesn't work. And we can even increase the number of neurons and layers, and it still doesn't work very well. And the reason why this is happening is because there's just simply not enough information for the model to figure out what to do. So it's like no matter how smart you are, with just these two inputs of X1 and X2, that's just not enough. And so one thing that we can do is actually increase the number of inputs that we have in general. So they call it features here, but basically what they are different inputs. If you give it a little bit more information, for example, x1 squared, x2 squared, as well as the sign transformations of the data, you'll be able to do a lot better. So since this is much more complicated, it takes a much longer time to train. As you can see over here, it's still doing a lot of changes, and it's changing somewhat slowly. But you kind of see that it's forming that little spiral over there, and now it's more prominent. And eventually it does a somewhat decent job of figuring out what the points should be. Anyways, I highly recommend you checking out this website. Literally at the top of the page, it says, tinker with a neural network right here in your browser. Don't worry, you can't break it, we promise. And so don't be intimidated, just mess around with it. It's really cool. So going back to the spam classifier that we were talking about earlier, what it does is it uses logistic regression, and the inputs are basically the words that appear in the message as well as their frequency. So for every single word that appears in the training data, it will correspond to a specific X. So for example, if we had the sentence, good night room, good night moon, and the word good night corresponded to X2, and the word room corresponded to X4, and the word moon corresponded to X1, then the input would look something like this, where everything else would be zeros. The model doesn't consider the meaning of the words or the order they appear, etc., etc. And the output would be the probability that something is spam. Now, as I mentioned earlier, the model isn't perfect, and so the role of an AI engineer would be to perfect this model. So some things that they could potentially do to improve the model would be potentially pre-process the inputs so that synonyms will map to the same input value. So we could achieve that by incorporating a thesaurus into the model that we have, or we could use sentiment classification to first map words to their meanings. We could also change the input so that it considers groups of words instead of just words on their own. So the word not bad would then be considered a single positive phrase instead of 2 negative words. Alternatively, we could also use a more complex model. And so these are the kinds of things that AI engineers think about. They think about the features, so the inputs, what features do we have, how should we modify them, what features should we add, which ones are useful, which ones not, how to scale the features so that they're equally or not equally considered, and what to do if the features aren't giving the right results. And we see a lot of that earlier in the example where we had to transform the x's so that we had x1 squared, x2 squared, as well as their sign transformations. And they also look a lot at data. So how do they collect it? What do they collect? How much data do they need? Does it match their actual use case? So for example, the spam classifier didn't work perfectly because the spam messages it was trained on usually involved dating sites, whereas the spam messages that I receive are very different since I'm not the target audience of date single local woman near you type of messages. And finally, there's also questions like what model do we use, and many more. So in conclusion, I really hope that the last few lectures were interesting and that they really helped demystify the field of AI. I really don't like how the term AI has now become a buzzword and everyone thinks that it's something super complicated, but in just the last 40 minutes, I was able to explain to you exactly how it works, and now you understand the theory behind it too. Thanks again for watching, and I hope you enjoy the rest of the quarter.